All right, so moving forward, our next statement reads, an ideal dipole is situated at the origin, its dipole moment points in a z direction, and is quadratic in time, i.e. P of t is equal to 1/2 p double dot t squared z hat direction. Okay. So with that, we have negative infinity to infinity is where the time domain is allowed, where p double dot is a constant. So use the method of 11.1.2 to determine the exact electric and magnetic fields for all r greater than 0. Calculate the power PR of t passing through a sphere of radius little r, and then find the total power radiated and check that the answer is consistent with equation 60. All right. Sounds like we've done this before. So for our solution in part A, write P of t is equal to Q of t, and then multiply that by d, or that is our typical dipole moment. So Q of t is equal to KT squared because it's quadratic in time. And so if that's the case, we have KD is equal to 1/2, or where KD is equal to 1/2 or P dot. So as in equation 1.5, what we see is that when we expand it, again, kind of a multipole expansion here, we have script r plus, script r minus. Kind of hard to see there, but yeah, by expanding that out, putting everything in terms of, k and t, we could factor the k out, square the fact that we have t evaluated at the retarded time, and now you see we have two reds. Well, they cancel out. We like that. We like cancellations, don't we? Okay. So in our next block, what we see here is that, again, they cancel because when you split up the fraction, the script r's cancel, and then that minus sign in the middle allows the two t terms to cancel. So good there. But with that being said, we can now factor out a t squared that came with the 1 over script r's. And then we could also factor out a 1 over c squared that came with just the addition of the script r's. That being said, we know from the multipole expansion what to expect the script r's to look like, i.e. r times 1 minus plus d over 2r cosine theta, and then 1 over r plus minus gives us the inverse of that, and flip the sign on the inside. Okay, cool. We've seen that approximation before, and quite recently at that, in question 24. So if we plug all these things in and see what cancels with it, or what combines, you see we get a combination here of 2d over 2r, so we're only left with d over r cosine for the t squared term. And then you see if we do the same thing here, we're left with d over r cosine for the minus of the script r's on the 1 over c squared term, and you get more cancellations. Here, both of them have a d cosine theta, so factor that out. We color-coded that again. And we could force the c squared factor by putting it into the t squared term. So we're cool there. With that being said, we substitute in the mu naught epsilon naught from the c squared. We combine the kd terms to the 1/2 p double dot naught, p naught double dot. And we cancel the epsilons, cosines there. We refactor out that square for the CTR minus 1, and now we're looking pretty good. Here, now we can move forward at least to the vector potential. And as the same goes from equation 15, if we let I of t equal dq dt, well, we know what dq is, so we can let that be 2k z hat, right? Or that should be 2kt actually, because if we take the time derivative of kt squared, then we get 2kt. So that should be a 2kt in that first line. And what that allows us to do is integrate the vector potential of this current. So that's why we have 2k evaluated at the retarded time. And now we just push everything through. dz happens in a symmetric fashion. We get d over 2 minus d over 2. So that minus sign combines them, and that's where we get the d there. And if we see we have a kd, we put the same substitution in. So we get u naught over 4. 2 times 1/2 rho or p naught double dot, and you see those 2's cancel. The retarded time, we just split up that fraction, so we get 2 over r minus the 1 over c So again, if we factor a 1 over c out and kind of force that factor, then we get a similar duplicate form there with that fraction of CT over R. All right, so it looks like we're good to go there. Now for the electric field, we know we need the negative gradient and the negative time derivative. So apply the derivatives accordingly. And let's note here that while doing so, for the gradient, we go to r hat and theta hat in the curly brackets, but we see that that 8 that we had from the scalar potential gets reduced down by a factor of 2, which is highlighted in the blue terms for the derivatives, just so we could factor that out in the next term with the fact that in the other squiggly brackets we have the derivative of the time derivative of the vector potential, and all that did was cancel c terms. But we have a mu naught p double dot over 4 pi in both of the squiggly brackets, so that's why we did that to factor it out. And I also highlighted here in green that all terms had a 1 over r in it. So now in that cleanup, we're left with a cosine c over r squared from the first derivative term in the gradient. Then we have a sine over 2 with the ct over r squared minus 1 theta. And then the z hat we just replace with our typical spherical coordinates. So after that, we just refactor everything, and we see that we get, I guess, kind of what we expected, actually. You know, at least with the cleanup side. We get a mu naught, p naught, double dot, 4 pi r with a squiggly bracket for the factors on cosine in the r hat and the factors of sine in the theta hat, but both of the factors in the bracket look familiar in structure. And if we want the magnetic field, take the curl. Again, only use the applicable components and derivatives instead of stressing ourselves out. So apply the derivatives carefully. We see we get in the second line on the next page, a lot of reds canceling negative signs. We like that. And then we have, after reduction, of course, we have the the c terms canceling after the 1 and 1s cancel. So hence the red. Other than that, that was a pretty quick derivative, and we're just left with a magnetic field of mu naught p naught double dot t over 4 pi r squared sine theta d phi, or not d phi, but phi hat. And then a quick calculation is found for the pointing vector. You notice that we just have E cross B, but a lot of the constants are similar, so we just tag them out. And we notice that B is only in the phi hat direction. So we just move that cross product from E cross phi to R cross phi and theta cross phi. Okay, so that's pretty much all that was there. We could factor out that sine theta from the B and just kind of tidy up those coefficients together. We see that one round of mu's cancel, and now we're just left with tidying up the pointing vector cross products. R cross phi goes to negative theta, and then theta cross phi goes to r. And the second to last line, we just go ahead and take the dot product of the dA, because we know we're going to have that in the next stage when we're trying to find power. So we see that the r's cancel, and we lose all, we lose the, what am I looking for? The dependency here on the theta direction. That's what I'm looking for, since we're pointing in the r direction for the dA. So we let that simplify down. Clearly here then in the next slide, our power, RT, goes from 0 to 2 pi, 0 to pi, because we're integrating over all angles, because we're on a sphere, of course. And then, let the calculus work its way. We get that 2 pi from phi, that 4/3 from sine cubed. We've seen that a million times as well. Let that reduce down. And then we see that we're left with mu naught, p naught, double dot squared t, over 12 pi r with the ct over r squared plus 1. Okay, if we were to evaluate this at the retarded time, just plug in t naught plus r over c and evaluate through. The only reason why we're doing this is now after we simplify the retarded time expansion and cleanup, now we can take the limit as p radius or p radiation of t naught. That works because we're setting the limit as r goes to infinity, So we're only left with the retarded time radiation. So if we do that, you let your calculus run through. You see we get a 1 in that first parentheses, and in the bracket, we're dividing by infinity. We have plus 2 divided by infinity, so all that survives, that limit, is that final plus 2. And hence, we have exactly what we expected with mu naught, p naught double dot, squared over 6 pi c. So, cool, a little bit messy, but nothing terribly difficult.